In this lecture, we'll be discussing intermolecular forces. And on the title slide, there's just a basic depiction of the intermolecular forces that we'll be talking about. Those are ion dipole, hydrogen bonding, dipole-dipole, ion-induced dipole, dipole-induced dipole, and finally the dispersion forces, also referred to as London forces or hydrophobic forces. Okay, so where we're going in this class, this lecture will be covering chapter 12, and we'll be talking about some phases of matter, intermolecular forces, and then some solid state chemistry. The next lecture, we'll be talking about solid state chemistry. Then we're going to be moving into nuclear chemistry, which is chapter 24, electrochemistry, chapter 21, and metallurgy, chapter 22. So just a little preview. All right. So, chapter 12, the first section, discusses the phases of matter. Okay, so each physical state of matter is what we refer to as a phase, which is a physically distinct, homogeneous part of a system. Okay, the properties of each phase are determined by the balance between potential and kinetic energy of the particles. The potential energy, that's in the form of attractive forces, tends to draw the particles together, and the kinetic energy, which is associated with the movement or velocity of the particles, will tend to disperse the particles. Right, so attractive forces, the intramolecular or bonding forces found within a molecule. We have chemical bonds, right, that are within a molecule, keep the atoms in that molecule together. Okay, the chemical behavior of each phase of matter is the same because that bond doesn't change given the phase, right? The hydrogen-oxygen bond in water is always that bond, whether it's in the solid form, liquid form, or gas form. The intermolecular or non-bonding forces that are found between the molecules, these are the ones that can change in the different phases. At least the strengths of these change in the given phases. So we all know the three main phases, right? They're gas, liquid, and solids. Okay, just a table depicting the attractive forces versus kinetic energy and the properties, the basic properties of each. I think we're sort of familiar with this. Gas has the most kinetic energy, so the attractive forces are very weak relative to that. Liquid, the attractive forces are stronger because the particles have less kinetic energy, at least less kinetic energy compared to gas. And in solid, they have the least amount of kinetic energy, so the attractions dominate the motion. Okay. So if we look at this table, now we're looking at the shape and volume, the compressibility, and the ability to flow. Right, so gas is very compressible. It has a very high ability to flow. Liquid has very low compressibility and moderate ability to flow. Something like water, you would say, doesn't seem very moderate, right? Because it flows pretty readily. But compared to a gas, its flow characteristics are much what's the word I'm looking for? Much more resistant to flow than something like a gas would be. Okay, and then finally solid. This is where you have almost no compressibility and almost no ability to flow because it's really maintaining its own shape and volume. Okay, and it doesn't conform to any container or that it's placed in. Right. Well, if something is in, let's say, a solid phase, it doesn't just stay there. It can transfer into liquid phase or even a gas phase, or vice versa. Okay. So phase changes are important. So if we look at gas to liquid or liquid to gas, as the temperature drops, or as we know from the ideal gas law, the pressure rises, the molecules in the gas phase come together and form a liquid in the process of condensation. So a gas going to a liquid is called condensation. The opposite process, a liquid going to a gas, would be called vaporization. Solid to liquid, that phase change is, liquid to solid. Phase change is freezing. The reverse process, solid to going to a liquid, is called melting, or the more technical term for that is fusion. And you can also kind of skip that liquid phase and do gas directly to solid or solid directly to gas. So gas directly to solid would be deposition, there we go. And solid directly to gas is sublimation. Right, so if you think about the some two familiar phase changes, this figure is shown in the book. One is deposition, where you have water vapor in the air. When it's so cold, it will just deposit ice crystals on like a window. Okay, so that's deposition. It's not going through the liquid phase first. It's going straight from the vapor phase in the air to the gas. And vaporization is something like when you're sweating, when it's hot out doing a workout or something, that sweat evaporating into the vapor phase is what's cooling you down. We have delta H's for phase changes, enthalpy changes for these phase changes. In some of these compounds, they're delta H of vaporization and delta H of fusion are shown here. Right, vaporization is always going to be larger because you're fully separating molecules apart from one another, going from a liquid to a gas. Whereas the fusion, you're going from a solid to a liquid, the molecules are still in close contact with each other and can interact with each other. Here is a roadmap of what the phase changes are and the names of each phase change. So if you ever forget, this is a good kind of figure to look at. So solid to gas is sublimation, liquid to gas is vaporization, solid to liquid is melting or fusion. Okay. And the reverse processes are shown here. Okay. So within a phase, heat flows is accompanied by a change in temperature. Since the average energy of the particles changes, kinetic energy, so the Q is, we can write an equation here, equals the amount times the heat capacity times the change in temperature. Okay, so that's within a phase. If we're trying to account for the heat changes with respect to a change in temperature. Okay, during a phase change, the heat flow the heat flow occurs at constant temperature, and the average distance between the particles changes. So the heat, if we're trying to calculate the heat for a phase change, it's just going to be equal to the amount of the substance times the delta H of that phase change for that particular substance. So in this figure, it's showing a cooling curve for water. And if look over on this side, if you start at 130 degrees at water vapor and let it cool, as it cools and the temperature's dropping, you're releasing heat. So the amount of heat released is going up along this axis. So you're releasing heat, the temperature's dropping within that phase. You reach now the temperature at which gaseous water turns to liquid water. So you get the phase change there. And so now the amount of heat released for this phase change, this gas to liquid phase change, is shown here. And that is a very large amount, right? When you're dropping 20 degrees in the gas form of water, this is how much heat was released. Now just changing the phase, you release this much heat. And this stays at 100 degrees. This is at a constant temperature. Okay, so that's the phase change. Right, and that would be the delta H of vaporization. Right. Okay, as you cool further in the liquid phase now, you go from 100 degrees to 0. Right, so you've released this much heat released to drop this much in temperature. Okay, and then you reach that liquid to solid phase change, again, constant temperature, and then in the solid you can continue to cool down. Okay, in a closed flask, let's say we put a liquid in a closed flask and create a vacuum on it and seal it off. There's going to be an equilibrium. So there's going to be a certain amount of the substance, the liquid substance, that goes into the gas phase above it. Right? And then it reaches an equilibrium, so the number of molecules going in the gas phase is equal to the number of molecules from the that are gas going back into the liquid phase. And this is referred to as a vapor pressure. So that's the pressure exerted by the vapor on the liquid until the pressure increases until the equilibrium is reached. At equilibrium, the vapor pressure is constant. Right, so a vapor pressure is measured like that. Okay? You have the liquid, put it in a vacuum, and you measure the pressure of gas that is above the liquid at equilibrium. So what factors affect that vapor pressure? Well, the temperature will affect it. So a higher temperature will mean a higher vapor pressure. The weaker the intermolecular forces, the more easily these molecules can enter the vapor phase, and thus the higher the vapor pressure will be. So weaker molecular forces equal higher vapor pressure. So things like hydrophobic solvents that only have dispersion forces as intermolecular forces in them will generally be much higher vapor pressures than will aqueous solutions, something like water that has hydrogen bonding interactions that are much stronger within that liquid. So it will have a lower vapor pressure than an organic solvent. And that's shown here. Okay, so the diethyl ether is something that is very hydrophobic, and well, relatively to the other two, it's hydrophobic, and you can see the vapor pressure shown here at a particular temperature is always higher for it compared to ethanol and water, which both have hydrogen bonding interactions available to them. Right. So we introduced the Clausius-Clapeyron equation And this equation is one that relates the vapor pressure to the temperature. So it's looks pretty complex, but really all it is the pressure equals negative delta H of vaporization divided by R, the gas constant, times 1 over temperature plus C. And the 2-point form is probably more widely used. So that's used when the vapor pressures at 2 different temperatures are known, right? So this form of it is probably one that you will see more or use more. Okay. This is just kind of explaining why that equation is in the log form, right? When you plot log of the pressure versus 1 over temperature, you get these straight lines, so they're linear relationships, as opposed to what we saw initially, right? How the vapor pressure is changing with temperature. It's not in a linear fashion, right? So these equations were developed to make it easier to deal with, so that you could plot it out and they could be linear, right? And then the slope of that becomes negative H vaporization divided by R. So the vapor pressure and boiling point. The boiling point of a liquid is the temperature at which the vapor pressure equals the external pressure. The normal boiling point of a substance is observed at the standard atmospheric pressure of 760 torr or 1 atmosphere. As the external pressure on a liquid increases, that boiling point increases. So that's why the boiling point of water is less in Denver than it is at sea level, slightly less, because you have less external pressure on the liquid water when you're trying to heat it up to boil it. So it boils at a little bit lower temperature in Denver compared to sea level. So one of the things that's helpful when looking at phases and phase changes of a particular substance is a phase diagram. So this is a graphic representation of the particular phases that you will find in that substance at a given temperature and pressure. So let me just put my laser pointer. And I should mention the lines, the dark lines that you see in the phase diagram are called equilibrium lines. They represent that phase change, okay, between solid and liquid, liquid and gas, solid and gas, under specific temperatures and pressures. Okay, so this is what a phase diagram looks like. This is for CO2 specifically. You'll have a pressure plotted usually on the y-axis and a temperature on the x-axis. And so how this is read, you can use it in a number of different ways, but let's say you're given a specific pressure and a temperature, you can tell, okay, what phase is that substance going to be in at those conditions. Or you can say, my process needs to happen at a specific temperature. What pressure do I need my reactor to be at to keep it in the liquid phase or the gas phase or whatever phase you're wanting? Okay, so that's one way you can kind of use it. The other way is to use it for on the lines, the equilibrium lines, and those are where the phase changes would occur at a particular pressure and temperature. And one point you'll note up here is when these three lines come together. So the solid gas interface, the solid liquid interface, and the liquid gas interface all come together at this point. That's called the triple point. And at that point, at that particular pressure and temperature, you're at an equilibrium between all three phases. Another special point is at the end up here, usually at very sort of high temperatures and higher pressures. It's what's known as the critical point. Okay, and that's where the distinction between a liquid and a gas, you can kind of think of it as like sort of disappearing. And above there, you're in what's known as a supercritical fluid, which has the properties of both a liquid and a gas. Okay. Here is another phase diagram. This time it's for water. Okay. And you'll notice some differences here with respect to CO2. One interesting point for water is that the triple point's much lower, but the other point is that this solid to liquid interface actually has a negative slope, and that means that the liquid is denser than the solid. Okay, if we go back, right, most substances, the slope of this line is positive, but in this case, for water, it's negative. Okay. You'll also notice that the critical point, much higher pressure, much higher temperature than for CO2. Okay, so let's try a practice with this. Describe the phase changes that occur when the temperature of CO2 is increased from negative 100 Celsius to 200 degrees Celsius at a pressure of 25 atmospheres. So let me get my pen. Okay, so to do this, we have to start at a temperature of negative 200. So let's just estimate that. Let's just say negative 200 is like right here. Let's call that negative 200. So that's the temperature, and the pressure was 25 atmospheres. So that's 75, 25, let's say that's about here. So this is where we're starting. Okay, and we're going, we're raising the temperature and keeping the pressure the same. So we're going to be moving along this sort of trajectory, straight line, and we'll come to our first phase change. Okay, now we're in the solid. As we're raising the temperature, we're still in the solid form. We get to this phase change. Now we're converting into liquid, so we are staying a liquid water till we reach this line. So at that temperature, which for water, this is for CO2, so this is not water. Don't really know what that temperature would be, but maybe we could make a guess about, well, that axis is very hard to guess from. Yeah. So we've moved into the gas phase, and then as you increase, you would increase up here until you reach the desired temperature of 100 degrees. Excuse me, I was supposed to go to 200. This was negative 100. Okay. But the point is you're starting in a solid and you're moving along a horizontal line. As you cross those equilibrium lines in the phase diagram, that is where you are changing in undergoing a phase change. If you're trying to calculate the heat associated with this, you would have to take into account, you'd have three regions in each of the phases where your heat would depend on how much you have of the thing, the heat capacity of your substance and the change in temperature that you made. So there'd be 3 regions like that. That'd be 1, 2, and 3. Okay. And then there'd be 2 phase changes here and here, where if you're trying to calculate heat from those, you'd have to use the equation amount times delta H of your phase change. Okay. And then you would just add up all, in this case it'd be 5 of those heats to get the total heat of that process. Okay, moving on to section 3, we're going to discuss intermolecular forces. Okay, hopefully this part is review. Okay, I try to cover this in my classes, at least a little bit. So we're going to be going into maybe a little bit more detail now, but hopefully you've seen some of these before and understand them, at least a little bit. Okay. If we look at the physical properties that are affected by intermolecular forces, melting points and boiling points will be affected. Right? They're going to increase as intermolecular forces increase. The solubility is affected. So solubility in things like polar solvents will increase as the polarity or the dipole of that substance increases. So if you have a stronger dipole, your solubility in a polar solvent will be higher. And finally, solid state structure some of those features of the solid state structure are going to be affected. And an example of that is how water expands as it freezes, and that's due to hydrogen bonding. So intermolecular forces arise from attraction between molecules with partial charges or between ions and molecules. So ions meaning full charges. Intermolecular forces, they're relatively weak, and that's compared to bonding forces because they're involving smaller charges that are farther apart, but they are still very influential in the physical properties of substances. Okay. We call them weak, but that means weak compared to a full chemical bond. Okay, they're still they can still be very, very influential. Okay. So if we're comparing some of the bonding forces, okay, so these are full bonding forces. Okay, ionic bonding, where you have a full positive charge and a full negative charge that are very close to one another. The energy of those is shown here, the energy range. Example of it would be sodium chloride. So very high energies. Covalent bonding is where your nuclei share a pair of electrons between them. And you can see that the energy now is slightly less than a true ionic bond. Okay. Example for this that was used was H2, so 2 hydrogen atoms sharing electrons. And finally, metallic bonding, which we don't really talk a whole lot about in this class, but it's thought you can think of it as cations that have delocalized electrons kind of running through them, and the energy there, it's similar to covalent bonding. Right. So those are bonding forces. Now we want to talk about the intermolecular forces. So forces that are not as strong as those bonding forces and are, a little bit further apart in terms of scale. Okay. So I think this is a good table to know for intermolecular forces. And it ranks them from the highest intermolecular force to the lowest in terms of strength. Right. starting with ion dipole, you could probably throw ion above this. An ion-ion interaction that is very close to one another would be considered an ionic bond. And I'm not sure there's many examples of this in chemistry, but in biochemistry, you can have a full charge interacting with another full charge on a different amino acid in a protein, that they're still, a decent distance away, so they're not making a full ionic bond. They're not close enough for that, but they're still full charges that are interacting with one another. Okay. But for this class, we can just consider ion dipole to be the strongest. Okay, and so that's where you have an ion, which is a full charge, interacting with a dipole, which is a partial charge. The typical energy shown here. So if you remember what a typical covalent bond would be, this would be something like 1/4 to 1/2 of that, something in that general vicinity. Right. Example here, something like a sodium ion interacting with water would be that ion dipole. Okay, the next strongest would be hydrogen bonds. Okay, hydrogen bond is where you have a polar bond to a hydrogen dipole. Okay, so if you have a hydrogen that's bonded to something that's electronegative, it's going to be very positive, and then it can interact with another very negative substance. So in the case of water, right, water can hydrogen bond with itself because it has both hydrogens and it has these lone pairs of electrons on the oxygen. And the typical energy in kilojoules per mole is shown. Hydrogen bonds are a dipole-dipole interaction, okay, but you can consider them to be the strongest dipole-dipole interaction. Okay, there are other dipole-dipole interactions, and that's the one that's listed next. That's where you have a dipole interacting with another dipole, so a partial charge interacting with a partial charge. Okay. Then as we go down, you have ion-induced dipole. So you can have something that it doesn't have a permanent dipole, but will have an induced dipole. So the example here is iron is our ion, a full charge. Oxygen doesn't normally have a dipole, but in the presence of a something like an ion here, it can get polarized and have an induced dipole. So the positive charge here can attract more electron density to this side of the oxygen and create a dipole on it. Okay. You can have a dipole-induced dipole where you have a partial charge then inducing a dipole, inducing a partial charge on something else. And then finally, dispersion forces, which are a little bit hard to explain, and I'm not going to expect you to really know the exact nature of what we call dispersion or London forces in this class. You can also refer to it as the hydrophobic force, but it's where you have, in a sense, it'd be an induced dipole interaction, if you want to think about it that way. Okay, so let's go through some of these in a little bit more detail. Okay, ion-ion interactions, basically an ionic bond, but maybe not quite as close together. Ion dipole, dipole-dipole, which the special type of that is H-bond, dipole-induced dipole, and finally dispersion forces. So collectively, dipole-dipole, ion-induced dipole, dipole-induced dipole, and dispersion interactions, these are known as van der Waals forces. So ion-ion interactions obey Coulomb's law. If you remember Coulomb's law, it's the charges multiplied by each other divided by the distance between them. So as that charge increases, the energy of the bond would increase, or the energy of the interaction. And as the distance increases, that energy of interaction will decrease. Interaction, if we look at ion dipole now, in the interaction between an ion and a partial charge of a molecule with a permanent dipole. So something like a salt being dissolved in water, we have an ionic substance that has these ion-ion interactions at very close range to one another. It can dissolve in, right, and those interactions are very strong. So why does that dissolve when you put it in water? Well, it's because you can have these ion dipole interactions that the water molecules can undergo and actually make it favorable to pull these ions away from each other, even though they have very strong attractive forces to one another, because you have, in this case, it's coordinated with 6 waters, all have that very that ion dipole interaction, right? That's making up for the loss of the ion-ion interactions. And if we go further, you have the what's known as the inner hydration sphere, where the water is interacting directly with that ion. And then you can have the outer, what's known as the outer hydration sphere, where you have water molecules that are interacting with the water molecules that are coordinating that ion. These networks get very, very complex and complicated, and that's why there's a lot of stability in this intermolecular force. Okay. Next up is dipole-dipole interactions, and these are interactions between polar molecules. Okay, polar molecules have permanent dipoles, and the positive side of one molecule's dipole can interact with the negative side of another molecule's dipole. And the hydrogen bond is a special case of this dipole-dipole interaction. It's actually the strongest. Okay, it requires a hydrogen atom that's covalently bonded to a strongly electronegative atom. So something like a fluorine, an oxygen, or a nitrogen. Those are the atoms that connect to the hydrogen that allow it to have a hydrogen bond. And some of those hydrogen bonds, types of hydrogen bonds, are shown here. All right, if we look at polar molecules in the solid form and the liquid form, they are, in both cases, in both phases, they are undergoing hydrogen bonding. Right, so there's this hydrogen bonding network at all times in polar substances. This figure shows a dipole moment with respect to boiling point, and you can sort of see that they are correlated. The higher the dipole moment, meaning the more polar something is, the higher the boiling point in general is going to be. So the hydrogen bond are possible, again, for molecules. They need to have a hydrogen, but it has to be covalently bound to a very small electronegative atom with a lone pair of electrons. So nitrogen, oxygen, or fluorine are the ones that are seen in hydrogen bonds. Okay. An intermolecular hydrogen bond is the attraction between the hydrogen atom of one molecule and the lone pair of the nitrogen, oxygen, or fluorine atom of another molecule. And how we depict that typically is shown here, where you have just a dashed line between the lone pair of electrons on one molecule and the hydrogen on another, right? And that hydrogen, again, it can't just be any hydrogen. It has to be a hydrogen that's bonded to something electronegative like nitrogen, oxygen, or a fluorine. Right, so hydrogen bonding and boiling point, right? How does, if this is a figure showing the different trends with respect to the periodic table of boiling points, and if we have the different elements in these groups depicted by the different colors here, bonded to hydrogen, the compounds they make with hydrogen, and plot out what the boiling points of them are. You can see that the ones here that are circled, these all form hydrogen bonds, and their boiling points are much, much higher. So as we go, let's just look at the red curve, family 6A. So oxygen, when it's bonded to hydrogen, the molecule it forms is H2O, water. That forms hydrogen bonds. It's a very high boiling point. If we go down that group now to the next lowest element, which would be sulfur, right? Its molecule it forms with hydrogen would be H2S, okay, and its boiling point much, much lower. Okay? And selenium and tellurium, they're follow the same general trend. So if you just use these and plotted what you'd expect that next boiling point for oxygen to be, it'd be somewhere here, but that doesn't take into account the hydrogen bonding, right? So when hydrogen bonds factor in, it raises that boiling point much, much higher, because you have stronger intermolecular interactions, and it's harder to separate those molecules in the liquid phase apart in the gas phase. Right. DNA also undergoes hydrogen bonding. This is a very important example of hydrogen bonding biochemically. Right. We have the complementary bases here, so I think, I'm not sure if you probably covered this in high school biology, but the bases A, C, G, T, G and C are complementary, and they form 3 hydrogen bonds between each other. And A and T form 2 hydrogen bonds. Right. Another biochemical example of where hydrogen bonds are important are in enzymes. Right? Remember, enzymes are proteins that catalyze reactions. So in this just generic enzyme, we have an active site, and that's where a molecule comes in. Molecule comes in, and then it interacts with the side chain of the protein in that active site, and you create hydrogen bonds with the side chains or the backbone of the amino acids in the protein with your substrate molecule, and those usually will stabilize the transition state, so that lowers the activation energy, and it allows the reaction to occur faster than it would without catalysis. Okay. We can look at the thermodynamics of this. So if you look at the uncatalyzed reaction, the free energy change, it would be shown here. The green would be uncatalyzed, so it has a higher barrier. The red, now you've lowered that activation energy because you stabilize the transition state via hydrogen bonding. And by lowering the activation energy, this reaction can occur faster. Right? You haven't done anything to the actual delta G, because the The free energy of the products and reactants are the same. All you've done is you've stabilized the transition state. And you can look at this in like a crystal structure of a protein and determine approximate lengths between certain amino acid groups and find, if something's within 4 or 5 angstroms, you can consider like a hydrogen. If you have hydrogens don't actually show up in the crystal structure, but if you have a nitrogen within about 4 or 5 angstroms of a carbonyl oxygen, you can sort of consider that as a possible hydrogen bonding place in the protein. Okay, so let's try another practice problem. Let's try drawing hydrogen bonds between molecules of different substances. Okay, so which of these substances exhibit hydrogen bonding? Draw examples of the H bonds between the 2 molecules of each substance that does. Okay, so let's look at A. Get my pen. So that's not it. Okay. So A is ethane. And looks something like this. You will see molecules like this more in organic chemistry, but what you do notice here is that there's no electronegative things like fluorines or oxygens or nitrogens. So this molecule is nonpolar. And will not be able to form hydrogen bonds. Okay, it has lots of hydrogens, but those hydrogens aren't attached to things like oxygen, fluorine, or nitrogen. And there's no unpaired electrons either. Okay, so no H bonds. Okay, B is methanol. Which looks something like that. Okay. Now you do have a hydrogen that is bonded to an oxygen, something that's very electronegative. And you have that oxygen group in there. So this will undergo hydrogen bonding. So we have, if we wanted to draw another one of these methanols, try to draw it so it lines up. Okay. So you can get hydrogen bonding interactions between, this is a hydrogen, between the lone pair on the oxygen and the hydrogen group on separate molecules. So these molecules can interact, right, and make sort of a chain of interactions. Right, but it's only that hydrogen that's connected and bonded to the oxygen. That's the only one that participates in hydrogen bonding. Okay, and finally C, I'll do that right here. Okay, C is a little bit more complex. And I'm just going to write CH3 for that. Those are not going to be participating in hydrogen bonds. Okay. This one, and I should show the lone pairs here, this molecule will it is polar. Okay, there are polar bonds with those hydrogens on the nitrogen, and we have lone pairs on this carbonyl, right? And you know, polar aspect to that. Okay, so this has different spots, many different combinations to do this. So these lone pairs on this oxygen can interact with a hydrogen that's connected to a nitrogen on another molecule. And a lone pair on, you know, let's say that oxygen can interact with that hydrogen. This nitrogen also has lone pairs, so it can undergo hydrogen bonding, right, with a hydrogen that's on another nitrogen. Whoop. On a separate molecule as well. So there's many different combinations in this molecule for hydrogen bonding. So polar molecules are pretty easy when it comes to intermolecular forces, and their intermolecular forces are pretty strong, relatively speaking. Now let's talk about the interactions that nonpolar molecules undergo. These are called dispersion or London forces, caused by temporary or induced dipoles in molecules. So an induced dipole is just a separation of charge in an atom or a molecule due to a momentary uneven distribution in electrons. A nearby electric field can induce a distortion in electron cloud of an atom. So for a nonpolar molecule, this induces a temporary dipole moment. So if you're, let's say you're close by an ion, you know, a charge, that can induce a momentary dipole in the electron cloud of a particular molecule that's nearby. Okay. When you're a polar molecule, you already have a dipole. An induced dipole field can really just enhance that existing dipole. So we're really not considering that. We're sort of just considering you either have a permanent dipole, or if you're nonpolar, you can have an induced dipole. Okay. So if we look at this from the figure in the book, you can have a case where you have two molecules that are nonpolar. If they come closer together, there can be a case where the electron clouds shift and induce dipole in each other. And thus now that you see that their negative end of one dipole is facing the positive end of the other's dipole. So this is sort of that dispersion force. The other option is where you have a polar molecule coming close to a nonpolar molecule, and just that dipole that the polar molecule possesses is enough to induce a dipole in the nonpolar molecule. Right, so the dispersion force, you can think of this as a momentary shift in electron density. A dipole-induced dipole is really just the proximity of a polar molecule creating that dipole. So the trends in this polarizability, and that's how easily these dipoles can be induced. Okay, for smaller particles are less polarizable. So smaller molecules, in a sense, are less able to have induced dipoles than larger ones. And that's because their electrons are just held onto more tightly. Polarizability increases down a group because atomic size increases, and larger electron clouds distort more easily. Okay? So as you go down a group, you can polarize easier. Polarizability decreases across a row because of increasing effective nuclear charge. Cations are smaller than their parent atoms and less polarizable. Anions show the opposite trend, right? Remember, once a cation loses an electron, you still have that same nuclear charge there, so the electrons that are left get held onto tighter. Anions are the opposite. You're adding one extra negative charge, so your electron cloud is generally bigger. So if we look at a case when atoms are far apart, the polar molecule and the nonpolar molecule or atom, when they're far apart, they don't see each other, so they don't really influence each other. When they get closer together, that's when that instantaneous dipole in one atom can induce a dipole in another atom. So if this is a polar atom or molecule, and these get close enough, this nonpolar one will have its electron cloud will be induced into a dipole to positively attract or have a stabilizing interaction with the polar molecule. And this process can kind of occur throughout the sample, and you can build a stronger network of these dipole-dipole interactions, or I should say dipole-induced dipole interactions. All right. The dispersion forces or London forces arise when an instantaneous dipole in one particle induces a dipole in another, resulting in attraction between them. A dispersion forces exist between all particles, increasing the energy of attraction of all matter. Okay, so these forces are there for everything, polar, nonpolar, but they're so much smaller than what a typical dipole-dipole interaction would be, or a charged dipole interaction, that they're sort of insignificant. But in nonpolar substances that don't have those intermolecular forces, these are the intermolecular forces that become dominant. Right. These dispersion forces are also stronger for molecules that are more polarizable. Okay. So if we look at in the periodic table trends in molar mass and boiling point, so the dispersion forces, remember, are stronger for larger, more polarizable things. So as you're going down a group, those dispersion forces are going to be larger, right? So what do you think that means with boiling point? Well, boiling point here shown in bold should increase, right? If you're getting bigger as you go down a group in the periodic table, your dispersion forces should be getting bigger, and that intermolecular force being stronger should make the boiling point go up. And so that's what we see. These numbers here, the bold numbers, are increasing as you go down the groups. The molecular shape can have an impact on this. So if we look at two structural isomers of carbon, hydrocarbons, So in this case, pentane, we have 1, 2, 3, 4, 5 carbons in a chain, okay? And in this molecule, neopentane, we have 5 carbons, but they're all 4 carbons, 4 methyl groups are connected to a center carbon. Okay. The boiling points are shown for them, and pentane that's in this chain form has a much higher boiling point. So why is that? Well, it's because this spreads out the molecule, so it has more surface area, and these molecules can sort of stack on top of each other in this W sort of shape. They can kind of, stack into each other, whereas those interactions just don't exist as much. The surface area kind of stacking just isn't the same with this tetrahedral neopentane. Here's a flow chart to determine the intermolecular forces in a particular sample. First, you have to decide, are there ions present or not? Okay, so if there are ions present, if there's only ions, that would be ionic bonding, assuming they're close enough. If there's ions in polar molecules, you have ion-dipole forces at play. If you don't have any ions present, okay, then you decide, are there polar molecules only? Yes, that'd be dipole-dipole forces. And if you have a hydrogen bonded to nitrogen, oxygen, or fluorine, then there'd be hydrogen bonding. If you have a polar molecule plus nonpolar molecule, that's when you can get dipole-induced dipole forces. And if you have nonpolar molecules only, that's where you just have the dispersion force. Okay. So another important aspect of the dispersion force, or another way we can kind of describe it, is as what's known as the hydrophobic force. And so I'm going to take a brief second here to kind of talk about a very important a place where the hydrophobic force becomes very important. In biology, we have cells, right? And our cells have membranes, and the membranes are made up of molecules that have hydrophobic parts to them and hydrophilic parts to them. So in this case, you have a very long chains of hydrocarbons that are nonpolar, and then you have a polar, very polar head group. You can arrange these to make a bilayer where the hydrophobic parts stick kind of towards each other in the middle of this bilayer, and then the hydrophilic polar parts stick out. And so those parts will be the outside of the cell and the inside of the cell, both places that are exposed to water. Okay. If you want to look at the thermodynamics of this, going from these are called phospholipids, single phospholipids in solution to phospholipids forming this bilayer, the delta H of this transition would be about 0 because there's no phase changes here and there's no chemical reactions occurring. Delta S for this process, if you're considering only the phospholipids, it would actually be negative, right? Because if these are just floating around randomly, if you stack them and order them in this bilayer, that's going to be, you're increasing the order, and that would be a negative delta S. So that's not exactly favorable, right? We have a delta H is about 0, and we have a negative delta S. So this doesn't seem like it'd be a spontaneous process. So how is life possible? We know we need cells to have life as we know it. So how does this happen? And so I'd like to discuss a little bit about that as we go on. Okay. Solubility, and we're going to talk about why things are soluble in certain solutions. So that depends on the relative strength of that whatever you're trying to dissolve in the solvent. So the solute is what we're dissolving. Solvent is the solution that we're dissolving it into. Okay. So the solute-solvent interactions compared to the solute-solute or solvent-solvent interactions. So you're hoping that the interaction between your solute and solvent is stronger than the solute-solute or solvent-solvent to be able to dissolve. One common phrase for this is like dissolves like, right? So if you have an ionic or polar solutes will be soluble in polar solvents. Non-polar solutes will be soluble in non-polar solvents. Right? The example from the book that they use, you have a water methanol solution is homogeneous because they're like dissolves like. They can hydrogen bond together. And when they're separate, methanol and water are both polar and they both form hydrogen bonds with themselves. So when you mix them, they don't miss a beat. They can make a homogeneous solution. They have similar intermolecular forces. On the other hand, if you have something like octane, which is a 8-carbon long hydrocarbon, which is very nonpolar, you try to mix that with water. Now they're not working with the same intermolecular forces, right? Octane it has dispersion forces, and water has hydrogen bonding. It's polar, so they're not going to mix, and that's when you don't get this homogeneous mixture. You get a heterogeneous mixture, right? So what are some terms for this? Well, we refer to hydrophobic. That means water fearing. That's something that the interaction that repels water or diminishes water solubility. Hydrophilic, on the other hand, means water loving, and that's interaction that attracts water or promotes water solubility. So sometimes, you kind of interchangeably use hydrophobic and nonpolar or hydrophilic and polar. Right? So if you have, you can have molecules that have both properties to them, right? You have, in this case, you have very long chain of hydrocarbon, which is hydrophobic, and you have dispersion forces going on here in this part. But then you have these OH groups on the ends of the molecules, and those are polar, and they're also hydrophilic. They can interact with water via hydrogen bonding. Okay, so you can have molecules that have both. And this is where the hydrophobic force comes into play. Right, so protein folding, what a protein is an amino acid chain. And as synthesized just in a straight chain, they're pretty useless. They have to fold up into their active form, and that determines their overall function. Okay. When they fold to kind of stuff away hydrophobic amino acids. So some amino acids are hydrophobic, some are hydrophilic. The ones here in black are hydrophobic. So when this protein folds, most of the hydrophobic amino acids are hidden away from water on the inside of the protein. So again, if we look at the thermodynamics of this, you have interactions between the side chains of the amino acids. When this folds, okay, there's positive interactions between them, things like hydrogen bonding between polar amino acids. Okay. The cost, the entropic cost of this is pretty high because you're in this form, you're more disorder, more range of motion. And when you're completely folded, there's very little range of motion. It's way more ordered. So you have a big entropic cost. The internal interactions, like hydrogen bonding, offset some of that, but the other part that's important to it is what's known as the hydrophobic effect, and that's what really allows and drives protein folding. So we come back to that question with our cell and our membrane. How is life possible? And that's really due to the hydrophobic effect. And what the hydrophobic effect is, if we think about these polar and nonpolar parts of the phospholipids, if these were just by themselves, one by one, in solution in water, water can't interact directly with the hydrophobic tails of these. So I'm going to draw some water molecules in red here. So just these little V's represent our water. Okay. Right, so the V would be an oxygen and two hydrogens, right? Okay. So the water can't interact directly with the blue tail here, the hydrophobic part of this phospholipid. So they have to form these very ordered cages around the hydrophobic piece where the waters are extensively hydrogen bonding to themselves, and they're very ordered in this cage, sort of isolating that hydrophobic part away from the rest of the water. Okay. So it's that ordered water shell or cage around that hydrophobic part that is really what is driving these individual phospholipids to combine, come together, and form this bilayer where the phospholipid hydrophobic tails face each other, because they create this region in here that's all hydrophobic, no water involved. And what that does then, when they do that, when they do come together, all these water molecules are then free to fly off into solution. And it's that increase, that big increase in entropy for those water molecules going from this very ordered cage to free in solution. It's that giant increase in entropy that is what's known as the hydrophobic force. So the hydrophobic force has to do with the water that is driven away when hydrophobic molecules combine together in an aqueous solution. Okay, and that is what allows the formation of these cellular membranes, which life requires. It's what allows proteins to fold, which again life requires. So this is, and it's also one of the weakest intermolecular forces, but it is responsible for life as we know it. So I think that's just an interesting observation about intermolecular forces with respect to biology.